So in this lecture, we want to talk about functionals with higher order derivatives. So thus far, we've only focused on functionals of the form I of u is equal to the integral from a to b of f, which is a function of x, u, and u prime, right? We focused on that thus far. So what we want to do here is evaluate a functional of the form I of u is equal to the integral from a to b of f and x u prime, but now it'll also, this f will also be a function of u double prime, okay, dx. Let's call that equation 1. So we're going to treat this as an example of how to handle functionals of higher order derivatives. Okay, so as before, we're going to carry out the first variation and set it equal to 0. Okay, so we would write delta I is equal to 0, and when we look at equation 1 and find out what delta I is, we'll see that it's the integral from a to b. Remember, there's no such thing as delta x, right? There's no variation in x. We're only looking at variations in u, right? So this becomes partial f with respect to u times delta u plus partial f with respect to u prime times delta u prime plus partial f with respect to u double prime times delta u double prime, okay? Integrated over dx. Let's call that equation 2. Okay, so we're going to proceed in a very similar manner to what we did with our original functional. Now we're going to integrate the second term by parts to get the following. We'll end up being able to write integral from a to b of this. That second term looks like partial f with respect to u prime times delta u prime dx. Integrating by parts, we end up with partial of f with respect to u prime times delta u evaluated from a to b minus integral from a to b of d by dx of partial f with respect to u prime times delta u dx. Call that equation 4, right? We've already done that once before, so hopefully that's familiar to you. Well, let me make a correction. Sorry, I need to make my numbers continuous, so let's call this equation 3. Okay? So, as you probably expect, that third term in equation 2, I'm going to need to integrate it by parts, but I'm going to need to do it twice. Okay? So let's do that. So let's write that down. Then we have the integral from a to b of partial of f with respect to u double prime times delta u double prime dx. So the first integration by parts is going to leave us with partial of f with respect to u double prime, now times delta u prime evaluated from a to b, minus the integral from a to b of d by dx, and now partial f with respect to u double prime times delta u prime dx. Okay, so now I'm going to go ahead and integrate this integral by parts, and when I do that, I'll just bring this first term down, partial f with respect to u double prime delta u prime evaluated on a and b. Okay, now let's do this again. This now looks like minus d by dx partial f with respect to u double prime times delta u evaluated from a to b, and then minus a minus is a plus, so this becomes plus the integral from a to b of now d squared dx squared of partial f with respect to u double prime. Now this will be delta u dx, right? Let's call this equation 4. So what we want to do now is we'll just substitute equation 3 and 4 into equation 2. Okay, and when I do that, I'll group the integral terms. I end up with the integral from a to b of that first term, which doesn't change, so that's just partial f with respect to u. The second integral looks like minus d by dx partial f with respect to u prime. And then this third term now has the integral component plus d squared dx squared of partial f with respect to u double prime, right? And then we'll factor out that delta u dx. So that's the integral term. So it's tempting now with our boundary terms to combine them, but you'll note that we have a delta u prime in one term and a delta u in the other, and then this term in equation 3 is a delta u. So we can only group the ones that have the delta u term together. So that becomes plus this quantity partial of f with respect to u prime minus d by dx partial of f with respect to u double prime, right? That quantity times delta u evaluated from a to b. And then there's one more boundary term right here, right, with this delta u prime. I'm going to have to write it below just for the sake of having room. So this then becomes plus partial f with respect to u double prime, delta u prime, evaluated at a and b. Let's go ahead and call this equation 5. So what are we going to do now? Well, hopefully you're thinking, oops, and I should make sure that this is equal to something, right? This whole thing is equal to 0. So now we can use the fundamental lemma of variational calculus to get the following. So the first thing we're going to do is remember that delta u is arbitrary, right? So this integral will be able to apply separately, and we'll end up with an Euler-Lagrange equation. So that's the first thing that we can arrive at. So the Euler-Lagrange equation for this problem is d squared dx squared of the quantity partial of f with respect to u double prime minus d by dx partial of f with respect to u prime plus partial of f with respect to u equals 0. Let's call that equation 6. This boundary term actually now has, we have to think about two different conditions, right? We can talk about the definition of u at this case, and also u prime, okay? So let's talk about boundary conditions. And I'll just remind you, each boundary now has two possible conditions. So let's look at the case for u, right? So either u is specified at the boundary or it's not. So here we go. So u is going to be either specified, right? And you know that that's an essential or a geometric boundary condition. Okay, or you could have the natural boundary condition, right? So if we look up here, if u is specified, then delta u on the boundary is 0, so this term goes to 0 because delta u must be 0. But if delta u is not if u is not specified on the boundary, delta u need not be 0, and then this other quantity must be 0. So the natural boundary condition in this case is partial of f with respect to u double prime minus d by dx partial f with respect to u double prime, right? Our condition is that must equal 0, right, on the boundary. So maybe I'll put a bracket around there and say that this is evaluated at the boundary. Okay? The other quantity that is either specified or not is now u prime, right? So let's look at u prime here. In the essential or geometric case, u prime is specified, right? And if u prime is specified, then delta u prime, this quantity, it's going to be identically 0, right? The variation there. And so this term will be 0 on the basis of that. But if it's not specified, then we require the partial of f with respect to u double prime to equal 0 on the boundary. So that would be the natural boundary condition that's associated with that. So del f del u double prime on the boundary, that's either a or b, that must equal 0. That's your natural boundary condition. Okay? So now what I want to do is I want to do just a really quick example. I'm actually not going to solve the differential equation, but I'm going to set up a beam problem that is of this form of having higher order derivatives, and we're going to get to the differential equation and then talk about what the boundary conditions mean. Okay, so here we go. Here's our example. We're going to consider the deflection of a linear elastic beam with a distributed load Q of x as shown below. Okay, so let's go ahead and draw this beam. So it looks something like this. Okay, and I'm actually not going to specify the boundary conditions at this time. So this, obviously, along the beam axis, that's x. If you want to call this the origin, then that would be, let's say, y. We have, let's say we have some distributed load Q here. Okay, so I'll try to draw these force vectors that are this distributed load on this beam. And we would say that this quantity is Q of x. All right. We'll also say that V of x is the deflection of that beam. Okay. I need to tell you a little bit about how we handle beams in terms of energy. The equilibrium configuration of any elastic body can be obtained by minimizing the total potential energy of the body. Okay. Okay, so in the case of the beam shown, we can write the total potential energy as follows. We typically call the total potential energy capital pi. So pi as a function of V, the deflection, is equal to 1/2 times the integral from 0 to L of EI, the beam stiffness, right, times the quantity d squared V dx squared, that quantity squared, minus Q times V. Okay, this is our integrand dx. Okay, call this equation 7. So that's the total potential energy of this beam, right? So we require that we want to find the V that extremizes this functional, right? So what we want to do is find the minimum total potential energy by finding the V that makes this capital pi the smallest, right? So what do we require? Well, we require delta pi to equal 0 for equation 7, where we're going to observe that the integrand of equation 7 is of the following form. F is equal to some function of, it looks like in this case, V and a V double prime. I don't see a V prime in there, or I don't see an X explicitly in there. Okay, so we have a functional that's of this higher order form that we just talked about. So now what we want to do is we want to use the Euler-Lagrange equation given by equation 6 in conjunction with this class of functional. Okay, so this would look like d squared dx squared of partial of f with respect to v double prime. That's really our variable now, right? Minus d by dx partial f with respect to v prime, right? Plus partial f with respect to v is equal to 0, but there's no v prime here, so a partial f with respect to v prime, that must be identically 0, and we're left with this simplified Euler-Lagrange equations for this problem, which is just d squared dx squared partial f with respect to v double prime plus partial f with respect to v is equal to 0. Let's call this equation 8. Okay, so, but given that we know what f is, right? F is equal to EI times v double prime, right? That's what d squared v dx squared is, squared minus qv, right? And then we have this 1/2 term here. Given that that's what f is equal to, and let's call that equation 9, right? We can compute partial f with respect to v double prime and partial f with respect to v. So partial f with respect to v double prime looks like, let's see, that looks like 1/2 times EI times 2 times v double prime. 2's cancel, and am left with the following: EI V double prime. Let's call this equation 10. Okay, I can do something similar and say that the partial of f with respect to v is now equal to negative 1/2 q, right? Let's call that equation 11. And now I'm just going to substitute 10 and 11 into equation 8. And I get a governing differential equation that looks like d squared dx squared of the quantity EI V double prime minus, minus 1/2 q, so that turns into a plus 1/2 q. So then minus 1/2 q is equal to 0, right? Let's call that equation 12. If I wanted to go further on this, I would have to assume that, let's say EI is constant, or I have to know their functions, right? So let's just go ahead and do that and say, assuming that EI is constant, then equation 12 becomes two derivatives of V double prime now gives me a V quadruple prime, which I'll just write as V parentheses 4 to tell you it's the fourth derivative. And I'm going to just divide by EI, and I'm left with, this equals to Q over 2EI, right? Let's call this equation 13. Okay, so you can look at this hopefully and recognize that this is a fourth order ordinary differential equation, but it's inhomogeneous, right? Because Q is actually, if I'm being explicit, is a function of X, right? So we have we'll need to solve for a homogeneous and a particular solution. We're not going to do that right now because I didn't give you enough information. But I want to just say that observe that the resultant differential equation that comes out of this Euler-Lagrange equation is a fourth order ODE. So remember, I didn't specify the boundary conditions, but we have the following options that we can choose. Okay, so let's kind of try to work through it like we did before. So I have some sort of statement on V, right? The deflection at each end. So here's V, and in the case of the essential or geometric boundary conditions, right? I could just simply have V be specified at the boundaries. Okay, if I don't specify it, then I have to have natural boundary conditions. So I'll have an or. In this case, we'll have the natural boundary conditions now. And those go back to what we talked about previously, right? If V is not specified, then I have the quantity partial f with respect to V prime minus d by dx partial f with respect to V double prime. That quantity equals 0 on the boundary. So let's work through this. We know that for this particular problem, there was no V prime explicitly in F. So this quantity goes to 0. So now we're left with negative d by dx of, we already computed partial f with respect to V double prime as well, right? That looked like EI V double prime, right? Equals 0. Or I can multiply by negative 1, and I can say that d by dx of EI V double prime, and I'll write it like you maybe learned it in beam theory. This is d squared V dx squared, right? That equals 0. Well, what is this term? Right, that's V. That's your shear term, right? So what we're saying is that V is equal to 0, right? This is a statement about the shear, right? So either we specify the deflection at that point or we specify the shear. Now, the other option, not the other option, we must also either specify V prime or it's not specified, and then we have a natural boundary condition. So let's look at that. In the case of V prime, it could be specified. Right, and what's V prime for a beam problem? That's just the slope, right? So so in the top case, we either have to specify at that point, specify the deflection or the shear. In the case of V prime or the slope, we're either specifying the slope or what? And you're probably thinking moment, and you'd be right? Because what's the natural boundary condition that we just proved? We said that the partial f with respect to V double prime must be equal to 0. That's the equivalent, right? And what does this look like if we substitute in our equations? This says EI V double prime, which maybe I would write as EI d squared V dx squared is equal to 0. And hopefully you know this from your sophomore level mechanics of materials class, as this is your moment, right? So what we're saying here is that the moment equals 0. Okay? So hopefully this is at least tying together a little bit of stuff that you've always known and always worked with, or at least for many years. And it's at least making sense now. So let me give you a couple just illustrations of what we could have, right? So we could have simply supported, right? And in the case of simply supported, here's our beam. Forgive my inability to draw straight lines. Okay, so there's one side, and we have this on the other side. And what are the boundary conditions? Well, on this side, and of course there's a Q on there, but let's just look at boundary conditions here. This side says V is equal to 0, right? Nothing can deflect. We don't constrain the slope, right? So we aren't defining V prime there. So what's the equivalent condition? The equivalent condition is that M, the moment, is equal to 0 there, right? So we know that this first term is, I'll put a G for it's a geometric boundary condition, while the M equals 0 is a natural boundary condition. We come over to here, and we also have V is equal to 0. That's geometric. And then also M is equal to 0, which is natural, right? So that's a real simple example. How about for a cantilever beam, right? So in that case, let's try to draw. We have some boundary. We have a beam that comes off of it here. Okay, something like that. And so what can we say about on this bound of that beam? Well, obviously V is 0, nothing's moving, right? So V is equal to 0, but also the slope is 0, right? It can't bend at that point. So V prime is equal to 0. So in this case, we have two geometric or essential boundary conditions, whereas at this end, what can we say? Well, we're not constraining the deflection, and we're not constraining the slope. So the equivalent, if we're not constraining the deflection, then we know that there must be a shear boundary condition. So that must be equal to, the shear must be equal to 0 there. That's a natural boundary condition. And similarly, there's no applied moment. The corresponding natural boundary condition for V prime would be that a moment is equal to 0, also a natural boundary condition. So there's just a couple examples of the kinds of boundary conditions and how they would be employed in this beam problem.